Okay, let's continue. Sven Bachmann will give his second lecture on the classification of interacting phases.
Thank you very much. So yes, I will switch gear a little bit. I talked about quantum Hall last time, which is an example of a topologically ordered state. And many times until now, we've already heard the word quantum phases or phases of matter. And so I want to give essentially some basic definitions specific to fermions here instead of quantum spins, as we've seen many times. And then once you have a definition of what you mean by a phase, you can try to classify them, and I will explain what that actually means. And if I have time today, I'll start talking about a particular symmetry-protected topological phase protected by time reversal. But we'll see whether we're going to have time this time. So the setting, so yes, it's a C-star algebra. So the algebra A is sometimes denoted CAR, so of H. Oh, actually, my H, I will take the H like this. So H is a Hilbert space. So you have to think of this the following way. H is the Hilbert space of one fermion, okay? And you want to create an algebra that corresponds to observables of many fermions. How do you do this? If my thing here accepts to work. So that's what's called the one-particle Hilbert space. Typically, you can have here, we will always think of H to be an L2 space. I will be in 2 dimensions. So over the lattice A2. So that's not necessary. You can build this algebra of any separable Hilbert space, but for us, it will be convenient to think of this one for today. And what is this algebra? Well, it's an algebra. It's a C-star algebra generated by elements denoted A of F, where F is an element of the Hilbert space H. These things are called annihilation operator. And so it's a C element A of F and an identity, and a 1 identity element. So you have one AF, and you have an adjoint. You have also the A star of F called the creation operators. And they satisfy the anti-commutation relation, which is A of F yips A star of G. So I will denote A star. It's the same as A of G star, okay? That this is equal. So you see, F and G are one-body wave functions, so they live in the one-particle Hilbert space. There's an inner product on this one, so it's going to be this. So Fg, where this inner product is in that Hilbert space, the one-particle Hilbert space H. What this symbol here means, so this is the anti-commutator of A and B. It's AB plus BA. Okay, the presence of a plus means, I think I forgot something. Times 1. Thank you, Bob. Right, so this is an element of the algebra, so this better be an element of the algebra, not a number, and it's a multiple of the identity. So this defines for me a C-star algebra, so it's very simple, right? What is it made of? You take these A's and these A stars, you multiply them together, that gives you monomials. You make linear combinations thereof. You get polynomials in these A's and A stars, right? And you take the norm closure of these elements, okay? So that's this algebra of canonical anti-commutation relations. It's the standard observable algebra for fermions, okay? By the way, so equivalently, and now I will be specific to that particular Hilbert space, little L2. You know, you can pick a basis now I will really take Z2 Cn. So these would be the functions that are 0 everywhere and just 1 at a site x that I denote by delta x, tensored with EI, x an element in the lattice, I in 1 to n. So this is a basis of that Hilbert space. So this is supposed to be an n. Right? So these are good wave functions and denote denote A xi, A of delta x tensor ei. Right, that's a good wave function, the one particle Hilbert space. I just denoted AXI, because that's what you see in any sort of physics textbooks. Okay? And so you can think now that you could also generate the whole algebra by just using those elements for all x and all I. Now that gives you a notion of the local. You know, we've seen so far it's very important to know what you mean by an observable localized in a set. So the local algebra are associated to a set lambda, a subset in Z2. Well, it's just the algebra generated by these guys, right? These AXI, but x only in the subset lambda and for all I. Okay? So we have, similarly to the fermion system, we have a C-star algebra, we have a notion of local algebras. Okay? In fact, you can rephrase the whole thing in terms of a spin system if you wanted. It's called the Jordan-Wigner transformation, which is very used in one dimension, not so much in higher dimensions. But just to say, it's, you know, it looks a little different, but overall, these algebras are very similar to each other. Good. So, right. So now on this, and Caroline already mentioned that word, there's parity, or fermion parity. So in that particular algebra, there's a particular automorphism of the algebra, if you want. You see, you generate the algebra as being polynomials in A's and A stars. So for any monomial, you can say whether it's even or odd, right? That defines for parity. So you define an automorphism. Define automorphism, which I will denote theta on A by, well, you just say that theta of A, let me pick any A of F, is minus A of F, right? And so, you know, it's in fact a star automorphism, so theta of A star is minus A of F star. You extend all of that so that it becomes a homomorphism, right? So that's fermion parity. That's called fermion parity. Fermion parity. Okay. And then you can have even elements of the algebra. Well, they're such that theta of A is A. So they made up, if you think in terms of polynomial, it's a polynomial where every single monomial is even. And you have, of course, also the odd elements of A. Theta of A is minus A. Now, of course, it's not true that any element is either even or odd. In general, an element of the algebra is a superposition of, or a linear combination of being in even or odd. Okay? So this will be this is an important automorphism, this fermion parity. Okay? Good. Right. I will also say if an element is either even or odd, I will call that homogeneous. Okay? All right. Good. So so far we had various notions of local observables, quasi-local observable, almost local observable. So I'm sorry, but I will again define this in a way which I think is consistent with everything we've seen so far. But anyway, is almost local or almost localized at a site X. So if, well, instead of being very explicit, I'm just going to say, if there exists a sequence AR, so R here does not label site, it labels a distance. There exists AR such that AR is in the local algebra. You have your site X, you have the ball of radius R around the site X. Okay, so these ARs are strictly localized in that ball. Okay. Such that, and you know, these ARs approximate A in a very efficient way. So in such that A minus AR is bounded above by norm of A, F of R, where F of R, you know, I will just write it this way, where R to the K, F of R, and I'll take well, let me take the limit as R goes to infinity is finite. So, you know, it's just another way to say that the sequence AR approximates A, right? But not in any fashion, in a very fast way, in a super polynomial way. So the important thing here is this rate of convergence, right? The quasi-local algebra is defined as the closure of the local algebra, you remember, in quantum spin systems. That just says I can write it as a limit of elements in the local algebra, but without any specification of the rate of convergence. So the almost local algebra has that specific thing on top. So they're not strictly local objects, but they're extremely well approximated by local objects, right? And this F of R, that just says it decays faster than any power, so I should have said for all K. For all K. When I start seeing looks like this, I'm thinking something is wrong. Was that the? Yeah, okay. So you could, you know, I could also have written here O of R to the minus infinity to use what we've seen many times, certainly within Caroline's talk. Okay? So that's the almost local as opposed to, and that fits Caroline's definition of almost local earlier today. Good. You know, sometimes you want to insist on exactly which function. You could say it's F localized if you want to specify which function you want, but it's rarely the case that the specific F plays a role. I just want something which is faster than any inverse power. Good. So I have an algebra. I'm not going to define a state. It's a state we now all know exactly what it is. There's an identity, so Daniel is happy. We have an algebra with an identity. So here's where I will be a little bit, I'll diverge slightly from what we've seen. I will define what is a TDI for time dependent interaction. So this, I think yesterday and this morning, we've seen that Hamiltonians are given by an interaction. An interaction is a map from finite subsets to self-adjoint element of the algebra, right? That are supported in that finite subset. You can work with it and it will be equivalent to this, but somehow this is quite often more efficient, or rather more convenient. So what is it? It's just a family of family of almost local elements that I will call Fx, may depend on a parameter S, x in Z2, such that, you know, Fx of S is almost localized at x. And we will assume that it's for the same function f for all x and even for all s. At s with the same function f for all x and s. You could relax this in a little bit, in a sense, a little bit like Bob did this morning, but for simplicity, I will take that. In fact, I will never have to use here S in all my applications will have to live in a compact subset of R. If you want really to extend that to all of R, maybe you'll have to have some sort of additional conditions here. But for simplicity, I won't do that. So these guys, you see, you have to think these are the interactions that are kind of localized around the site, or the, you know, around the site X. But unlike the interactions we've seen earlier, which are strictly localized, but you can have them of arbitrary large size, here I like to just, to each site X, I associate one of them. So you could, a little bit as Bob was describing this morning, you could, by slicing these things, recreate an interaction in the sense we've seen this morning. And from any interaction, you could sum up terms in a smart way to reproduce an object like this. Okay? Just turns out for me it will be easier to use these TDIs. Okay? In fact, in the case, let me just remark, if no time dependence, these are sometimes called zero chains. And Nikita Sopenko will probably use that language later during the week. It's a language that is a very good language. I would like to say that all of these things, they have been rediscovered and reinvented many times. They all originate this sort of almost locality, and all of that originates in the algebraic quantum field theory in the 60s. And they've been redefined and okay, so all of this is not really groundbreaking. Okay, so we have now almost localized observables. We have TDIs, which you should think of as time-dependent Hamiltonians, okay, in the language used this morning. And if I can take this down. So why do we want to have TDIs? Because we want to have the corresponding automorphisms of the algebra, the dynamics that these Hamiltonians generate. Okay? Now, you see, on purpose, the parameter I use is not t, it's s. Again, that echoes Bob's talks, because you shouldn't think here of that parameter as real physical time. It is a parameter which may be time, but in fact will be different things. It will be a flux, for example, later on. Okay? So now, if you have a TDI, you have a corresponding LGA, again, a notation introduced by Kapustin and Sopenko and company for locally generated automorphisms. It's the taus we've seen before, right? These are just the families alpha S associated to a TDI F. It's a map from A to A. That is the solution of alpha S F of A is A plus I. So I write the integral equation instead of the differential equation. Alpha U F of U A du. It's the integrated version of the Heisenberg equation. Okay? You can pick whichever you want. For simplicity of mind, again, I will take, these have a dependence in time, so you can ask, well, when does that all make sense? Right? When do you have a unique solution to that sort of equation? So for simplicity, you can take that each of them, so they're made up of fx. So fx of S, that is a good element of the algebra, and I'll take that to be continuous in S with respect to the norm. Again, you could relax this, but let's in fact, in some cases, you have to relax this, but it's okay. Oh, I have to say something more. In fact, in my definition of a TDI, I'm sorry, I'll get to your question. Add, very important, a TDI has that fx of S or they are all even. So my Hamiltonians are even elements. Again, it's not all examples you can think of have that property, but the ones I want to use will have that property. Okay? All right, so Hamiltonians are even elements, and they generate the dynamics, which I will call an LGA. Note, although the setting is not exactly what we've seen earlier, and the important, why do we care about this? Because an LGA satisfies a Lieb-Robinson bound. Okay, so they take local elements and map them to almost local elements. In fact, here you could even write it in the following fashion. You could say alpha SF of A. I didn't introduce a notation, but A log, as opposed to A log, is the algebra of almost local observables. And the Lieb-Robinson bound, you could state it as the fact that this algebra of almost local observables is invariant under the action of this family of automorphisms. Okay? So I will think of Lieb-Robinson bound in those terms. They take local or almost local elements and map them to, again, local and almost local elements. Okay? Of course, if you take an element here which has a decay function f, after evolution, the decay function will be of the same family, still faster than any polynomial, but a different function f. Okay? But that fits my definitions of the almost local observable. Good. So now I have all ingredients I want. You seem very confused. Yes? No. Okay, very good, very good. Not yet. Okay, okay. So, but you didn't seem confused.
I still had a question.
Yes.
So should I be thinking the capital F in the automorphism?
Yes.
Some of these fx's on finite.
Oh yes. So when I write this, it's a good question. So Daniel refused to write this, right? He wrote delta of A, but so here really the definition is this: it's sum over x, fx of u and A, and you can prove that if this is local or almost local, right? This sum here is convergent in norm and defines a good element of my almost local algebra, and so I will define the limit of that sum as this object, which Daniel would have written delta fu of A times I think, or minus I, right? So I will write a commutator. You know, it's a convention. The commutator, if you think, is just a notation for this derivation. Good. So, you know, yesterday, I think it was Marvin Key who gave us a definition of a phase. Now there's this phase. There was a big set of Hamiltonians. So this is one way of doing it. Here I will do it in another way. For me, a phase will be a set of states. In fact, Marvin went back and forth between whether it's a set of states or a set of Hamiltonians. So you can make different choices. I think at the end of the day, the natural choice is the one I choose. So it's a set of states. Okay? So in order to do that, I will define an equivalence of states. Okay? So I will say that a state omega is equivalent to a state omega prime. So I have an algebra. For now, the algebra is fixed. I look at two different states over the algebra. If, well, there exists an LGA alpha, I will not always bother writing the corresponding TDIF, right? So when I say an LGA alpha, that means there is an interaction that generates this guy, such that, well, maybe once I will do it, such that omega prime is obtained from omega by the evolution with this locally generated automorphism for time, and the convention is to take time 1. So it's a finite time. Okay? So that's a definition. It's a good definition. It gives you an equivalence of states. Now, you have to be careful, because you will see and we've heard of other definition of equivalence. So this sometimes is also called automorphic equivalence. Okay, because these two states are related by an automorphism. In fact, a particular automorphism which is particularly local. It's generated by a local Hamiltonian. Okay? You will see, however, this notation, probably even in this week, for meaning unitary equivalence, which says that the two corresponding GNS representations are unitarily equivalent. So this is not, so I will not unitary or even or quasi equivalence. Okay? It's not the same. In fact, you see, you have to think of two states are unitarily equivalent. I think this was even this was proved, or stated at least, if they are somewhat equal at infinity, right? If you go far out away, they look on any observable the same, or up to epsilon, okay? Now, these two things, you see, this is a Hamiltonian. That Hamiltonian lives everywhere in space, including at infinity. So this changes the state here absolutely everywhere, including at infinity. So in general, omega prime really differs from omega not only locally here, but also far out at infinity. And therefore, in general, there's no reason why two states that are automorphically equivalent are also unitarily equivalent. In general, this is wrong. Okay? So just be careful when you see this sort of equivalence relation. Okay? Yes?
How do I go back and forth between states and Hamiltonians if the Hamiltonian has degeneracy?
So you see, so my whole point here will be to say that the Hamiltonians are irrelevant. You see, have I said anywhere that the state is a ground state? No. These F that generates the flow, so to say, they have nothing to do with a physical Hamiltonian. Neither omega nor omega prime are ground states of that. So the Hamiltonian that I've introduced this far, there will still be actual Hamiltonian, but so far, they're just there to generate these deformations. So in fact, you know, this is, in a sense, this is the right notion of homotopy of states. Yes, so two states are unitarily equivalent. So I don't know, U omega prime, if pi omega, the GNS representation, is unitarily equivalent to pi omega prime, which means they both live in the same GNS Hilbert space. Okay, so that's one way to think, which again means that they're locally maybe different, but globally the same. They're thermodynamically the same. So
the unitary lives in the local.
which unitary? So here?
Yeah.
No. No, that unitary here is a unitary that lives in the representation. It's a different thing, right? Now maybe you can play some Caddison trick at some, depending on the situation, to get an actually unitary in the algebra, but in general it's not. So let me just stop a little bit here. You know, most of it, like, if you ask a topologist when you want to classify things, you know, very often, and things have to be invariant under deformations. Well, there's a notion of homotopy behind. The deformations are given by some continuous maps. And so here, and we had, I asked this question yesterday, you know, you also want to sort of construct a homotopy theory of these states, right? And you want to define homotopy classes. So you would like to define some families of states, right? Like a continuous path of states that interpolates between omega and omega prime. So here you see, if I were to put an S here, that defines for me a family of states, and they're all equivalent in this sense. So this is some sort of homotopy. However, it's not a good, there's not, and I'm a barbarian, you know, I'm not a mathematician, so I don't exactly know. But this is not a homotopy associated to continuous maps with respect to some given topology on the set of states. In fact, the experts sit here, there, and everywhere, and Daniel, they looked at homotopies of states, like, but not defined like this, but just defined by continuous families of states. You can do that with two natural topologies, the norm topology, and you get an incredible amount of classes, so too many. The other natural topology is the weak star topology, and you get only one class, so that topology is too weak. And you know, this is the right notion. That's how you get the right classes, physically the right classes, except it's not really given by a topology on the set of states. And it's an interesting question whether you can somehow construct a good homotopy theory, and I don't know the answer to this, based on that sort of families of states. You know, there is some sort of continuity, of course, right? These are weakly star continuous, but it's more than that. You have this, it's generated by a local Hamiltonian, so this notion of preserving locality is completely important. The Lie-Robinson bound is crucial here. Okay? Just to say that this is a little bit of an open problem, if you want. I mean, this is, I think, the right definition. Construct a nice mathematical homotopy theory around it is an open problem. Yes?
What's a simple example?
Any that we've seen. This morning we saw the Heisenberg spin 1/2, or the Heisenberg Hamiltonian. It's an LGA, except the particular terms are very, very local. They just sit on just two nearest neighbors, but it's a very good LGA. You could think of a long-range Heisenberg Hamiltonian. So instead of having Sx, Sx plus 1, you have Sx, Sx plus j, but with a coefficient that decays sufficiently fast in j. So in fact, super polynomially fast in the distance between. That would be also a good TDI, and the corresponding dynamics is the LGA. Okay? Good. So that's equivalence.
Question.
Yes?
What if you have two states on 1D that are related by conjugation?
So this does somehow this definition excludes explicitly translations. So you have to be able to smoothly deform things.
But I would want to call them in the same way.
So you could, and with respect to that, now you see here's yes. So I think here's what you could do. I will do more stable equivalence. So if you stack with another thing, I think I think you can implement translation if you stack with you first stack another algebra and then translate using the other algebra. I think you can do that continuously.
It translates the absolute.
Exactly. Yes, I think you can do that. So it would be. I think it fits, but I'm not sure. I think it fits the notion of stable equivalence, not equivalence. Yes.
So, I guess
Yes.
about the so I guess the that you're the autonomous bring up that come from Hamiltonian. I also think of like the states that come from Hamiltonian.
No.
So I'm trying to just
No. So exactly. I mean, my point is, please disconnect states and Hamiltonians for now. I'm trying to classify states and some families of states. I will make further assumptions, which might be that they're ground states of gapped Hamiltonians, but or have properties such as gap. But for now, I don't. The notion of equivalence and all that has nothing to do with a Hamiltonian. My goal is to classify states. Whether this is the right thing to do or not, I don't know, but at least it's a clear thing. I'm not mixing Hamiltonians and states. I'm talking about states. So just like in homotopy theory, you may know this, right? If you take the Möbius strip is topologically non-trivial, but if you twist it twice, it's topologically trivial. However, in 3D, you can try at home, you cannot untwist it, right? If you take your piece of paper, you twist it twice, paste it back, you cannot untwist it. But you can untwist it if you embed this in R4 or R5. I'm not exactly, I think in R5 you can certainly do it. Right? So in a sense, you need to be able to do these smooth deformations to embed your problem in a larger space. Okay? That's sometimes called stabilization, and I will define stable equivalence. We've seen that also in Marvin's talk yesterday by saying, well, I can do the same up to stacking everything with a product state. Okay? So stable equivalence. So omega on an algebra A, omega prime on an algebra A prime. And what is my notation? Then we'll say omega is stably equivalent with omega prime. So you see now you can compare states on different algebras, right? So if there exists an A tilde and A tilde prime. So all of these are CAR algebras in the same fashion, right? And product states omega 0 on A tilde omega 0 prime on A tilde prime, such that if you stack omega with omega 0, then this one can be deformed with omega prime stacked with omega 0 prime. Okay? So you allowed yourself, in a sense, to enlarge your state space, but not in any way by adding what would you think of as a trivial state, namely a product state. Okay? So that's a notion of stable equivalence, and you need it even in the non-interacting setting, actually, to do deformations. All right. Okay, but once I have that, I can make I have this notion of equivalence, and my goal is to classify the equivalence classes under these equivalence relations. Okay? And one way to do it will, of course, be to try to construct invariants, so numbers that I can associate to any equivalence class and that are constant over the class. Okay, and I will want to do that later on. So definition, a state omega is stably, no, my God, stably SRE for short range entangled if omega is stably equivalent to a product state, where omega 0 is a product. So convention for the rest of my talks, any state denoted omega 0 is a product state. Okay? Yes?
Do you carry your equivalence on the side?
No, I mean, you see, for this to hold, the algebra here has to be the same as the algebra there. Right? So you have to embed them both in the same algebra overall. But since A and A prime don't need to be the same, okay, you count the dimensions. Okay? Good. So that's the definition of short-range entangle. Caroline mentioned many times invertible phases, invertible states. So that's a different thing than that. It's a slightly different universe where you don't stack with the products, but you're allowed to stack with other states. I will not use that, so that's why I'm not going to define this here. Good. Good. So, and you could say, another definition that I could have made actually before this, a quantum phase is an equivalence class under the equivalence relation, the stable equivalence relation. Yes?
Sorry, is this the same thing as invertible?
No. You're forcing me to say it, right? So stably SRE is what? Up to stacking with a product state, I can deform to a product state. That's short-range entangle. Invertible is up to stacking with another state, which in general is not the product state. I can deform the two things together to a product state. So if you think of the product as being the neutral element of your structure, then what you stack with is the inverse. Okay? You can put bigger words than that on it. Okay? But it's what you stack with which is the difference. So for us, I always stack with a trivial thing, namely a product state.
Now I lost fermions along the way, but if I wanted to understand this absent fermions, are there conditions on the C-star algebra?
I mean, you see, the C-star algebra has to have a nice locality structure, right? Because I have to have this notion of product state, so to say. But that, of course, applies totally well to lattice, to quantum spin systems. You see here, I made the extra assumption that the TDIs, so the Hamiltonians, are even. So in fact, I essentially bring myself back to spin systems. Okay? No, no, no.
So in this formula, there's a how to define product state.
Yes, a product state. So it's a good point. So product state, omega 0 is a product. So I will say a pure state, omega 0 is a product state if the restriction of omega 0 to any local algebra AX is again pure. This is one way to define purity. Okay. You see, if you do a bit of quantum information theory, you know that if a state has entanglement, well, you see this by tracing out and looking at the state on only one subsystem, and even if it was pure before, then because of entanglement, it's mixed afterwards. So this is the somewhat algebraic version of that. Hmm? Yes? Oh, yes, yes, yeah, yes. So I will not do that, but you can. I mean, there would be a whole story to be told about entanglement entropy. It's, in a sense, also a little bit behind these definitions of why we take that as our definition of a phase. Okay. These LGAs, for example, if you know that, if you have a state which satisfies an area law, it's conserved under LGA evolution, for example. So, but yeah, as I said, that's a slightly different story. Good. I think I will end up getting this thing on my head at some point. And because it's recorded, it's going to be on the web for the rest of the life of the universe. All right. Good. So we have now our notion of phases. I want to introduce one more thing, namely symmetries. Symmetries will play an important. When should I stop?
So in 8 minutes, you still.
So at 10.
No, at 3:50.
At 3:50. Yes, exactly. Okay. So symmetries. So I will have an action of a group G on the algebra A, and we'll always assume that the action is on site. So it's a local action in the sense that for all x in my lattice Z2, I have a map. It's a family of automorphisms labeled by the group G. So gamma x of A, right? So I will just say that it acts on the algebra at x, gives me back an element in the algebra of x for G in G. What does it mean to be an action? Well, that gamma G of gamma H is gamma GH. So my group, I denote it here in a multiplicative fashion. OK, so this acts at each site. And by formal tensor product, this extends to the whole algebra, OK, and at all sites. So all my symmetries are going to be doing something like this. The groups that I will have in mind is either G is U1, that's charge conservation, or G is Z2, or for time reversal. So extend to all of. You see, you can extend that to finite tensor products of these guys, so to the local algebra, and then by continuity or boundedness to all of A by density. OK, good. So you see, now that I have an extra player, I have not only the algebra and the state, but I have the symmetry. And so all of these things, the Hamiltonians, the LGAs, you can again ask that they satisfy some invariance. So now we can define, stable or not. So I put that stable in parentheses. Stable equivalence, or stable G equivalence now. Of states. So omega is stably G equivalent to omega prime. If what? Well, So, well, first of all, in order for all of this to somewhat make sense, the states themselves are supposed to be invariant. So omega is invariant on the action of the group in that fashion. You know, for all g, omega prime, the same thing. Okay, so both states are G invariant. And so you see, this symbol means there's an LGA that intertwines between omega and omega prime. So if they're G equivalent, that LGA itself is invariant under the action of the group throughout the deformation. Okay? So omega, it will be stably equivalent to omega prime, and the TDI, you know, that underlies this definition, is G invariant, namely gamma G of fx of s is fx of s for all x and s. So the Hamiltonian, the interaction terms, if you want to use these words, all of them are invariant under the action of the group. Okay? So that's this notion of G equivalence. Now you see, now I have more constraints, right? In when can I relate two states? And so in general, I have more equivalence classes. Okay? So these, now I can start making, you know, all of these. I think these are words that have been used in this school already, but I wanted to give at least a version of the actual definitions that you can make that are somewhat consistent. Now, so still a definition, a G-SPT phase for SPT for symmetry protected topological phase, topological order, is what? Well, first of all, these are trivial if you do not insist on the symmetry. So there are, so a phase is a subclass of SRE state, right? So these states are trivial. They can be deformed to a product state. But now the phase is a G equivalence class, you know, within of states. Okay, so all of these states in a GSPT phase, they're all deformable to product, right? But now, so in particular, they're all deformable to each other, you know, through the product. Now the question is, if you take two such states, can you, and they're both invariant under the action of the group, can you deform one into the other by preserving the symmetry throughout? And it turns out sometimes you can and sometimes you cannot. I mean, this question a priori, maybe you don't, there's no more phases, right? It could be. Turns out it's not the case. So in general, there are true subclasses of the SRE states in here, okay? And these are the symmetry-protected topological phases. And you see, when I say these words, I always have to first say in my head, what symmetry am I considering, okay? So these SPT phases depend on the group G that I pick, okay? Good. So I will conclude with words. Now that I have a definition, I mean, it's always like this, right? It was a little bit boring. I just made definitions. So now you want to actually get a hand on this. How do you get a hand on these? Well, the natural way is to try to find invariants. So things that I can associate to a state, which will tell me, are you in a trivial GSPT phase or not? You know, I can compute it somehow or not. An example is, it's not exactly in the framework of SRE state, but you know, in general topological phases, the Hall conductance is such an index. If the Hall conductance is 0, in fact, you can prove that you're stably SRE. You're not SRE, but you're stably SRE. if the Hall conductance is non-zero. So it's, it's something you can compute, you can even measure, and it will tell you whether you're SRE, so in the trivial phase, or not. You can do the same thing for GSPT phases. We will look at time reversal invariance because it's just nice. And we'll again try to construct an index which will tell us whether I'm in a trivial SPT phase or not. And you can ask the second or the first question. In a sense, this work was already completely done in the context of non-interacting phases. The key word here is Kitaev's table. So Kitaev gave a complete classification of the phases for non-interacting systems. And you can say, OK, so what happens if I add interactions? Is this table still valid or not? OK? So that's also part of the motivation of why you want to understand these interacting phases. And in fact, Kitaev himself, after providing the table of non-interacting phases, also provided an example of an interacting situation where two elements that are in distinct phases in a non-interacting setting become connected in an interacting setting. So these phases, the non-interacting phases, are, in a sense, not always stable under the addition of interactions. So these are all questions that you would like to answer. And what I will do next time is precisely characterize the Z2 SPT, so where Z2 is a time reversal invariance SPT phase for interacting systems. And there it will just generalize the non-interacting results. And I'll stop here.
Are there questions? Yeah.
So this might be an annoying question, but in your definition of the stable G equivalent states, you have that they're stably equivalent, but your group action is in principle taking place on the tensor product, right? So is there a canonical way that you're thinking of extending
No, so
it?
you're actually free to pick your group action in this definition. I mean, I'm not, are you worried about the stabilization or not? Because otherwise the group action,
Well, yeah, because your TDI is
yeah, so you start
the tensor product.
You start with a group action. Now, the group action you put on the tensor on the product state, you're free to pick it. It could be trivial.
Okay, so it could be the trivial
trivial
action.
Yes,
Okay.
absolutely. There again, you have subtleties, right? You can make different definitions.
So for the actions we consider, would you care about non-singly generated groups? Like any type of group would yield a
take your,
meaningful-
let's say, locally compact group. So I actually have in mind compact groups. But SU2, if you want, most of the examples, I mean, as I said, my favorite examples, physically important one is U1, because it's charge. The one I will deal with is time reversal, which is essentially Z2, or version of Z2 if you want. So Zn or products of Zns, for example, are the groups that show up a lot. Other compact groups, in a sense, not so much actually, because subgroups thereof are more important. People don't necessarily look at all of SU2, but just Z2 cross Z2. That sort of subgroups are usually considered. But definition, you can take anything you want.
Would it be meaningful to have like a non-abelian symmetry?
Oh, absolutely. Yeah. So abelianness is not required anywhere here.
I see. And just one last quick question. So for the stable equivalence definition, should I compare this with like more von Neumann equivalence in the K-theoretic setting, where you like take finite amplifications?
Maybe. Again, I'm not sure. So I'm not sure. Here, you can think. So here's a concrete example. If you do, if you want to deform vector bundles, so it's more related to the strip, right? If you want to deform vector bundles, sometimes even vector bundles that are equivalent in the sense that there's an isomorphism of vector bundles, you cannot deform them like this. You need to embed both of them into a larger space, in the Grassmannian, and then deform within the Grassmannian. So that's somehow where this is coming from. So it probably has an analog in K-theory, which I don't know.
I see, but this amplification can be infinite dimensional.
Yes, absolutely. Yeah. It's arbitrarily large. Yes.
All right. Thank you very much.
Microphone.
So, why consider fermions here? Like the second half of the talk completely independent. So why
So
the setting?
all of these definitions work perfectly fine for quantum lattice systems. I introduced fermions because that's the algebra I will work with next, because it's the second time I say it's important that I have fermion, you know, that I have fermions last time because t square had to be -1, which I also didn't use here as well. So, but next time I promise that I will actually use something about fermions, namely the time, I will need time reversal, and the time reversal symmetry squares to parity and to fermion parity. So I will actually need fermions. All my results would be completely trivial if I had bosons. In fact, the time reversal invariant SPT phases for bosons, there's only one, but for fermions, there's two.
Thank you. So I guess if you're always working with compact G,
Yeah.
do you get like the, because so gamma G is supposed to also be linear, I guess,
Yeah,
presumably.
yes,
Okay,
yes,
so
yes.
then like you get semi-simplicity of the set of SRE states, is that right? If G is compact?
I think there's too many notions that are being mixed here. You know, the notion of SREs related to deformations which have.
Yeah, but
that has
I
nothing
mean,
to do with the
isn't
group,
isn't
so.
I mean, isn't this so aren't isn't this just a, this is just a group representation, right?
It's a group representation. So,
So
you know, if you think it's easier to think it for quantum lattice system, at each side you have a matrix algebra. So you're looking at the representations of your group on that matrix algebra. It
Yeah.
might be anything. It might be trivial. It might be irreducible or not.
I see.
It does.
So
That doesn't matter, right?
So
here.
then the SBT phases are going to be labeled by EREP labels, and
So
then, and whatever multiplicity label you have, I guess, is that. Like if you have
yes.
semi-simplicity, I
think
guess.
yes.
Yeah. Okay.
So when choosing your single particle Hilbert space, you
Yes.
like the internal degrees of freedom are Cn.
Yes.
Would this also work for an infinite dimensional Hilbert space on each side?
No, that's where things become tricky. You know, again, fundamentally, everything I do relies on locality through Lie-Robinson bounds. So if you have an algebra where on each side you have an unbounded Hilbert space, you know, a little bit like you describe, then everything collapses, or almost everything collapses. So that's why I always take a finite number of degrees of freedom. You think of that as being fermions with spin. That's the natural thing to consider here.
Okay, I think that's a good point. And for starting now the coffee break.
Coffee break.
And
yes.
we will resume at 4:20.
Okay.
So, thank you.